Good morning, everyone. Thank you for joining us today. In our last deep dive, we explored how to safely manage AI risk in the enterprise. But you know that entire conversation really comes down to something even more fundamental, the data itself. Data is the fuel for modern AI, but the most valuable data? It's often our most personal. And this creates this powerful tension, a real privacy paradox, right at the heart of the AI revolution, which is exactly what we're going to unpack today.
So this is the big question, right? On one hand, you've got these incredible algorithms that get smarter and more capable with every single piece of data they consume. On the other, we have this non-negotiable, essential right to privacy. So how do we square that circle? How do we reconcile these two forces that seem to be pulling in completely opposite directions? Today, we're going to move past just talking about the problem and really explore the powerful technological solutions that are emerging from the field of privacy-preserving machine learning.
All right, so here's our game plan. We're going to start by understanding why the old ways of protecting data just don't cut it anymore. We'll look at what I call the anonymization illusion. Then we're going to get into the really cool stuff and do a deep dive on 3 groundbreaking solutions: the mathematical muscle of differential privacy, the decentralized genius of federated learning, and the amazing data doubles created through synthetic data. And finally, we'll pull it all together to see how these tools really help us solve the paradox. Okay, let's get into it.
Okay, Section 1, the anonymization illusion. Look, to really get why these new solutions are so brilliant, we first have to understand just how badly the old standard failed. I'm talking about a technique that for years everyone just thought was good enough: anonymization. So why did this traditional method of anonymization fall apart? Well, for the longest time, the standard practice was pretty simple. You'd take a data set and just scrub it of things like names, social security numbers, addresses, what we call personally identifiable information, or PII. Everyone just assumed, hey, once the obvious stuff is gone, the data is safe. But in today's hyper-connected world, that assumption has turned out to be a really dangerous illusion.
And the story that absolutely shattered this illusion is the Netflix prize. So back in 2006, Netflix released this huge data set of movie ratings to try and spur some research. And they did what they thought was the right thing. They took out all the names. But some very clever researchers at the University of Texas had this key insight: data is social. They figured, sure, your Netflix ratings might be anonymous, but your movie ratings on a public website like IMDb probably aren't. By cross-referencing the patterns between the two datasets, they were able to successfully re-identify people in the anonymous Netflix data, exposing their entire viewing history. This was a huge wake-up call. The lesson was crystal clear. In the age of big data, your so-called anonymous data is never, ever truly anonymous.
That failure of simple de-identification is precisely why we needed a whole new paradigm. Which brings us to our first solution, Section 2, differential privacy. And pay close attention to that subtitle: a mathematical guarantee of privacy. This isn't just a guideline or a company policy, it's a rigorous, provable, mathematical definition of what privacy actually is.
So what is differential privacy, really? Like, what's the core idea? And then how do you actually take this mathematical guarantee and build it into a real-world system? Let's break it down.
At its heart, differential privacy is all about plausible deniability. Here's a simple way to think about it. Imagine a researcher asks you a sensitive question. Instead of answering yes or no directly, you first flip a coin. If it's heads, you tell the truth. But if it's tails, you flip the coin again and answer yes for heads, no for tails. So your final answer is randomized. The researcher has no way of knowing if your answer is the truth or just the result of a random coin flip. You have plausible deniability. But, and here's the magic, if they collect thousands of these noisy answers, they can mathematically subtract out the randomness and still get a super accurate estimate for the population as a whole. Differential privacy just formalizes this idea into a solid guarantee that no one can tell for sure if your specific data was even in the dataset to begin with.
So how do we put this into practice? Well, in the classic centralized model, you have a trusted curator. Think of it as a gatekeeper to the sensitive data. An analyst comes along and submits a query, like, what's the average age of patients in this hospital database? The curator computes the exact answer, but, and this is the absolute key, before it sends the answer back, it injects a very precise mathematically calibrated amount of random noise. So the analyst gets back a noisy answer that's statistically very, very close to the true one, but not identical. That little bit of added noise is just enough to completely mask the contribution of any one person, giving us that formal privacy guarantee.
Now, what makes this so powerful is this concept of the privacy budget, which we represent with the Greek letter epsilon. You can think of epsilon as a knob you can turn, a tunable dial that forces you to make a deliberate trade-off. If you set a low epsilon, you're adding a lot of noise. That gives you an incredibly strong privacy guarantee, but your results will be a bit less precise. If you set a high epsilon, you're adding just a little bit of noise. Your results will be much more accurate, but the privacy guarantee is weaker. Every single query you run spends a little bit of this budget, forcing organizations to be really transparent and intentional about how much potential information leakage they're willing to accept in exchange for useful data.
Okay, so that centralized model is great, but it has one big dependency. You need a trusted curator. What happens when you're working at a massive scale, like with millions of smartphones, and there isn't one single entity you can trust with all the raw data? Well, this challenge led to a really big innovation, pioneered by one of the biggest tech companies on the planet.
Apple really championed what we call local differential privacy, and honestly, it's a total game changer. The big idea here is that the noise gets added at the source, right there on your device, before any data ever gets sent out. So for example, your iPhone wants to learn about new slang words or popular emojis. Instead of sending the raw text you type, which would be a colossal privacy violation, the operating system applies differential privacy right there on your phone. It randomizes the information locally. Only this now privatized little snippet of data is sent to Apple. Apple servers then get millions and millions of these noisy, individually meaningless data points. But when you look at them all together, in aggregate, they can filter out the noise and spot the emerging trends, all without ever knowing that you specifically typed that word. It's a brilliant way to learn from the crowd without ever having to spy on the individual.
So that's differential privacy. Now let's move on to our second major solution, which tackles this problem from a completely different direction. Section 3, Federated Learning. And that subtitle says everything you need to know, bringing the model to the data. This is a radical flip from the traditional approach of sucking up massive amounts of user data into a central server.
All right, so what's the big idea behind federated learning, and how does this whole decentralized approach actually play out in the real world? Let's get into the mechanics.
For decades, the entire mantra of machine learning was, get all the data, bring it to one giant central server, and train your model there. Federated learning completely flips that idea on its head. The raw data, your personal emails, your private messages, your photos, it never ever leaves your device. Instead, a lightweight version of the AI model is sent to your device to be trained locally, right where the data lives.
Let's just walk through the cycle real quick. First, a central server sends out a generic global AI model to millions of devices, like your phone. Then, your phone takes that model and trains it just a little bit using only your on-device data. Now here's the really important part. Your phone doesn't send your personal data back to the server. No way. Instead, it just computes a tiny summary update, basically just the learnings from your data. Each device sends only that small update back to the central server, which then averages out thousands of these updates to create a new, smarter global model. And then the whole cycle repeats, constantly improving the model for everyone without ever centralizing the sensitive data that was used for training.
You've probably seen this in action without even realizing it. The most famous example is Google's Gboard, the keyboard on your phone. Google wants to get better at predicting the next word you're going to type. It does this with federated learning. Your phone downloads the latest global model, improves it locally based on how you type, and then sends back an encrypted little summary of the improvements. The result is a win-win. The global model gets way better for everybody, but your private messages and emails never, ever leave your phone. And it's worth noting that companies often combine this with differential privacy, just to add another powerful layer of security on top.
Okay, so we've covered mathematical guarantees and decentralized training. Now it's time for our third solution, which takes another tack entirely. Section 4, Synthetic Data. And I love this subtitle, the high-fidelity data double. The thinking here is pretty straightforward. If using real, sensitive data is just too risky, well, why not create a super realistic, completely artificial alternative?
So what exactly is synthetic data? And more importantly, how in the world do you generate a data set that's totally artificial but still captures all the subtle statistical patterns of the real thing? Well, the answer lies in one of the coolest tools in the entire generative AI toolkit.
We do this using something called a generative adversarial network, or a GAN for short. A GAN is actually made of two competing neural networks. First, you have the generator. Its only job is to create fake synthetic data that looks as realistic as possible. Then you have the discriminator. It acts like a detective, and its job is to tell the difference between the real data and the generator's fakes. So these two are locked in this constant battle. The generator gets better and better at fooling the discriminator, while the discriminator gets better and better at spotting the fakes. And this cat-and-mouse game goes on until the generator is producing synthetic data that is so realistic, the discriminator is basically just guessing. At that point, you can lock the original sensitive data away in a vault and use your highly trained generator to create a safe artificial dataset that has all the same statistical properties, but with none of the individual privacy risk.
Okay, that brings us to our final section, resolving the paradox. We've looked at three really distinct but also complementary technologies. So, let's pull all these threads together now and see what kind of path they lay out for building AI systems that we can actually trust. So after exploring the failure of anonymization and digging into these three really powerful techniques, what's the one big idea? What's the key takeaway about this whole privacy paradox? The key takeaway is this: we now have a powerful toolkit. This field of privacy-preserving machine learning has given us a completely new paradigm. We've got the mathematical guarantee from differential privacy, the decentralized approach of federated learning, and the safe replicas from synthetic data. And together, these tools let us move away from that old, simplistic mindset of just more data is better to a much more sophisticated, responsible one. Smarter, safer data is better.
And this is really the final thought I want to leave you with today. This is not a zero-sum game. The core message is that we don't have to choose between pushing AI innovation forward and protecting the fundamental human right to privacy. These technologies are giving us the technical foundation for a much more trustworthy AI future, one where we can learn from all our collective data without having to compromise our individual secrets. Thanks for joining me for this explainer. I really hope you'll join me next time as we explore the human in the machine, balancing autonomy and oversight. Once again, thank you for joining, and if you found this analysis valuable, please subscribe to our channel, Tech, AI, and Beyond. We'll see you next time.